Okay, now that we've got the basic formulas down for speed, velocity, and acceleration, we're going to focus on the vector aspect of these by looking at a graph of how we come up with the values for the slope to get our, in this case, velocity. We're going to take a look at a graph of distance on the y-axis and time on the x-axis. We'll look at some data and plot the points. We're going to do this together. And then the slope of the line is going to be y2 minus y1, which would be, in this case, d2 minus d1, over x2 minus x1, which becomes t2 minus t1. So this is called a graphical analysis, what we are about to do. We're going to use a graph to come up with our equation. We're going to come up with an equation in the form of y equals mx plus b, where y is the y-axis, which will be the distance, m will be the slope of the graph, which will be our velocity, and x will be our time. Our x-axis is the time, and then we're going to try and get this through the origin. No, we're actually going to get it through the origin, and that means then that we will have no value for b. That will just drop out. So this will be a very simple equation to use to come up with other pieces of information. So we're going to look at the graphical analysis of a constantly moving car that is being measured in an experiment to determine the speedometer is functioning properly. So we use a constant time change and measure the distance it has traveled for each time span, and here are the data. Okay, so we got 6 seconds. It's measured at 23.6 meters, at 12, 47.5, at 18, 73.2, and so on. You want to pause and get this written down before we go on to the next step. That might be a good idea, so you follow along what I do. Okay? Okay, welcome back. Now what we're going to do is we're going to graph the distance versus time on the next page on the smartboard. Okay? So let's do that. The first one is 23.6 at 6 seconds, so we can kind of estimate and be pretty, and I like using big fat juicy dots because my estimation skills are not the best, and besides this is a smartboard pen which has no hint of any kind of accuracy involved in it. It's always off a little bit here and there, so we're going to do this. It's going to be really close to 25, so I'm going to put it just below it. Big fat juicy dot there. We're also going to put a dot on the origin because that at 0 seconds it's not moved any place, so it's 0 distance. So all these graphs will start at the origin. Next one is at 12, it's 47.5. So here's 50, 47.5 is slightly below it, although more so than the 25. So this is going to go, I'd say, probably somewhere in the neighborhood right there. It's 73.2 for 18, so 18, 73.2. That's going to be really close to it. 24, 95.9. That's going to be kind of low on this end here. So there's that right there. I'm going to put that, say, right about there. And then at 30, it's going to be 120. 120 is going to be 4/5 of the distance between these two, so that's going to be right there. And here's 30, so I'm going to put that right there. Now I intentionally picked data that's not going to make a nice, clean, straight line graph because in life that's not how it works. Life is messy, and you have to deal with the irregularities of human interaction. It's never precise. So no big deal. So what we're going to do here is we're going to start the origin. And you can see these will kind of fluctuate around. These are not too bad down here, but this kind of goes crazy right here. So what I'm going to do, generally if they're like all over the place, we'll pick a point in which we'll find a good portion of the dots on one side and on the other side. So if I pick this point to go through right here with this, I'm going to get a couple on the bottom and a couple on top, or maybe 3 on the bottom, but really close and 1 way off on over here. And I think that's what's going to happen here. So we'll play around with this and see what this looks like, and then I'll come up with So it looks like two are pretty much on the same line. These two are really close down here, and that's above. So that's a pretty good representation right there. If you can't get them all to line up, which rarely happens actually, you want to get it such a way where you're going to get a fair representation of what all the data is. Unless you know you have one really crazy outlier, which I would say that one probably is right there, because it's so far away from the line from the others, that this actually is a pretty good one even without that dot being included in it. We'll just say somebody was not paying attention when this was done. So, next thing we need to do is to determine the slope of this graph. Okay, like I said, because we are going to be using y equals mx plus b. And like I said, the y-axis is going to be the distance, so that's going to be d. The slope is what we get from that, we'll come back to that. X-axis is t, so this will be times t. And plus b, because b is 0, that's just going to be completely wiped out. So the slope becomes really important to this. So let's do that. Let's go ahead and use these 2 points. I would use the origin in this, but since these 2 points are pretty much on the line, I'm going to use them to find the slope. So this is going to be 18. Actually, it's 18.0 according to what I gave you on the chart. So let's use the exact same numbers. X first is 18.0, and then the Y is 73.2. And then over here, this point here is 120, or I'm sorry, is 30.0 and 120. It's probably not a bad idea to include the labels, just so we have the labels in the final analysis here. So this is seconds and this is meters, this is seconds and this is meters. So M is going to be, I'll take this is the 2, so this is going to be x1 and y1, and this is x2 and y2. So that's how I'm going to treat this here. So this is going to be 120 meters minus 73.2 meters over 30.0 seconds minus 18.0 seconds. Okay? So, let's go ahead and do that. That bar thing, right there, 120 in parentheses minus 73.2 divided by parentheses 30.0 minus 18.0 close parentheses, and I get something stupid because I must have punched in something totally incorrectly. So let's find out what I did. Oh, somehow I accidentally hit the plus sign in the end. I didn't mean to do that. So I'll just hit the delete button and then try again. And I get 3.90. Going 3 feet, 3.90. And then the label then is going to be meters per second. So my overall equation is going to be, and that this is going to go right there. D equals 3.90 meters per second times T. Okay? So that's what we're going to use for our analysis for what they call extrapolations and interpolations. And what we're going to do is a couple of interpolations. And what that means is this. Interpolations mean you're picking a point somewhere within the range of the data that you collected, which is what we're going to do. If you want to extrapolate, you can go like past the graph over here, pretend like the line's extended, but you don't have to graph it because this equation takes care of all your graphing now. You've done a really good representation with the dots here. So this is a fair representation of what the relationship is between distance and time for any points because this is a straight line. So let's go back to the problem. And it says, what does the slope mean? Well, since you have meters over seconds, that means you are dealing with velocity. And how can you tell? Well, how can you tell? Is because it is what the label of slope is. That's the fact that you get a label that represents slope tells you that you are indeed dealing with slope. This means that the slope of a d versus t graph represents the velocity of the car. Now, let's do a couple of interpolations here. First one, in the graph and using the slope you determine, we're going to use the equation. What is the velocity of the car after 20 seconds? So we'll do that and then we'll come back to this one. So what is the velocity of the car after 20 seconds? I'm sorry, that's not a very good way of putting it. I should say, what is the distance of the car? So when you get these sheets, it'll be corrected. And then over here, the question you should be asking is, how long will it take to travel the 37.5 meters? So that's what we're going to find here. All right. So go back to the equation. We got 20.0 seconds. So I'm going to do this in blue because I like blue. Distance equals 3.90 meters per second times 20 seconds. The seconds cancel out, so that's going to give you meters. Multiply that out, and you get 78.0 meters. So in 20 seconds, you're going to go 78.0 meters. Okay? Go back to the problem and do the second part, and that is how long is it going to take to travel 37.5 meters. Okay, so go back over there. I'll use a different color for this, I'll use red. The formula is D equals, but we know the D here is, what did I say it was? Forget. 37.5 meters, all right. 37.5 meters. So 37.5 meters is equal to 3.90 meters per second times time. Okay? So I'm going to solve this problem by dividing both sides by 3.90 meters per second. That completely cancels out here. The meters cancel out here. And now you've got second in the denominator of the denominator, which puts it right into the numerator. Yay, yes, that's what we want. Go ahead and handy calculator is 37.5 divided by 3.90. And we get 9.62 seconds. Now, using the formula helps, but let's just kind of double check and make sure it makes sense based upon the graph that we did here. All right, for this one here, we went to 78 meters. 78 meters is somewhere up here. So if you follow that across over here, I'll use the same color blue for this so you can see what happens. Right? Kind of estimating here, and it's going to hit somewhere around there. And that looks like it's going to be just past 18 seconds, and sure enough, it's 20 seconds. So yes, that's a pretty fair way of representing it. Now, you'd rather use the equation. This is just eyeballing, and my eyeballs are horrible. So I wouldn't trust any answer I come up from an eyeball. I prefer the mathematics part of it. And when we do these problems, you're going to be using equations. For the other one, 37.5 meters is halfway between these two right there. And this is going to come down here, and as you see, it's going to be slightly more than halfway across. How slight? Well, we just use equation, we can figure out how slight, but it looks like about 9.5, somewhere around there. So this confirms it. This is 9.62, it says.